Hello guys, Nikhil this side, and today I'll talk about time series analysis and also the case study on time series analysis using air passengers data. So let's start with the introduction. Takeaways from today's session. What all things we are going to learn about it. So we have introduction and then component of time series, then evaluation metrics for time series, forecasting, and then hands-on. So what is time series? Well, time series data is an ordered sequence of values that collectively represents how a system, a process, or even behavior changes over time. Goal of time series analysis is forecasting future values based on previously observed value. We can in short say that the past values influence present value. Time series is concerned with analysis of data over time such as daily, weekly, monthly, or yearly. Let's, for example, take sales of cola. We In order to predict the sales of cola, we need to take time as a major factor, because if we don't consider time and we keep on manufacturing cola like uh, there was no stopping, but you might be at a loss. Why? Because when you say sale of cola clearly associates with seasonal aspect of time, right? So when there is a hot weather, or if the climate is hot, sunny, and if you are living in some hot climatic region, these are the kind of places or situations when the sale of cola will rise, and other time the sale of cola may be stagnant or it may dip. So we need to consider time as a major aspect of any data. Up until now, we never considered time as one of the important aspects, because we were just considering time, handling of time is very crucial task. It's a very big deal. So in order so let's proceed further. Like, what are the things that we can do with time series? Well, to be honest, we can analyze historical trend. We can also predict, what's the state of system at some point, and try to visualize and predict what it will be in the next point of time. We can also do the real time monitoring and troubleshooting with the example. Troubleshooting as in we can, like, for example, take COVID cases. Now, what we are doing, we are analyzing the pattern using time, like 3 months back, what was the scenario, how the cases rose, what were the symptoms, and then now again we are taking, uh, after 3 months of time, we are still trying to figure out how to resolve this issue, right? So these are some of the areas where time series comes handy. Apart from that, there are use cases which we can consider, like predicting the sales of tickets, then also stock market prices. These are the areas, where time series comes majorly into picture. So let's proceed further. When do we not use time series? Well, to be honest, we don't use time series when the data is constant, or we have the data fits a known function. Well, let's just say data is, what do we mean by values are constant over a period of time? Well, that means that the mean, variance, everything related to the statistics for that data is constant over a period of time. There is no change in that, and since there is no change, we can directly come to the conclusion that the things that were yesterday, that same thing will be today, because the line is a constant line. And then next is when we use a known function. So if we use a known function, like, just let's just say that of a line y is equal to mx plus c. Now we know that the data fits this line, so we can come up with constant and slope, and then we can predict the next value. There is no harm in that. We can directly predict it. So these are the types where we do not use time series. Let's move ahead. What are the components of time series? Well, there are five components of time series. We have level. Level component of time series is the position of data. Uh, or you can say level is the average value in the series. Then we have trend. Trend is the component in which is gradual increase or decrease of data, indicating the direction of data where it is heading. The trend may be increasing trend, linear decreasing trend, non-linear increasing or decreasing trend, or something like that. Trend is one of the important factor component of time series. Next we have is seasonality. Seasonality is just like a short-term cycle which keeps on repeating every season. Again, as I mentioned earlier, the sale of cola, well, that is associated with the seasonal aspect of time, isn't it? Let's proceed further. Cyclical. Cyclical is a gradual, long-term up and down, potential irregular swing of the data. The pattern repeats irregularly over time. Then we have random error. Random error is a very gradual. I mean, it's like a random increase and decrease of the data for a specific period of time. For example, let's just say there is a new Macintosh software launch. At that time, we can see that the sale of the Macintosh machines gradually increase. I mean, randomly increases, and then later on, as the hype goes down, the sale also comes to the neutral. So, no, note here, level and random error are one of the mandatory component of time series, while the rest of them are optional component. Next, we move ahead to decomposing a time series. Well, decomposing a time series can be sort of as a thing which breaks down a time series data into different components. We decompose time series in order to extract vital patterns of time series data, which are often difficult to detect through visual inspection. We, so when we break down or decompose the data, we can come to the conclusion whether in do we want to retain or remove such component. I mean, if they are not highly affecting the data. How do we decompose the time series? Well, we have two model, additive and multiplicative model. In additive model, the variance does not change over time, and it is constant. So we add up the different components of time series here. In multiplicative model, variance is an increase, keeps on increase just like seasonal aspect, and we have multiplication. The original series is multiplied. I mean, product of trend, seasonal, irregular components. Next, moving average. Moving average is the average of uh, elements. Moving average is the average of subset of elements in a certain amount of time. Let's understand this with an example. Like we have data here, month, expenses, and moving average, and we have kept window size as 3. So for this January month expense, we don't have any previous 3 data. So we cannot calculate the moving average for the January month, same for Feb month, same for March month. But for April month, we have previous 3 data, and we can add up these 3 data and divide it by 3. Calculate the average and put it here. So this is the moving average for the month of April, considering previous 3. Now when we consider May month, we will consider the month of April, March, and Feb data. Add up and create average and place it here. So and so on. This keeps on repeating. So this is the way we calculate the moving average. Moving average is one of the important aspect which we consider when predicting values in the time series analysis. Let's move ahead further. Evaluation metrics for time series. We have two evaluation metrics: mean absolute error and root mean squared error. Well, mean absolute percentage error is just like loss function for regression problem in machine learning. It is given by the formula mentioned below. Moving further is root mean squared error, and it is the root. Uh, it is given by the formula RMSE is equal to square root of 1 by n summation of actual minus predicted whole square for the interval t is equal to 1 to n. Lower RMSE implies the better prediction. So the lower the RMSE, the better the prediction, and also it depends on the scale of the data. Stationary versus non-stationary data. A stationary data is one which has the properties such as mean, variance, and autocorrelation, all constant over a period of time, while non-stationary data has exactly the opposite. It keeps on changing over time. So why are stationary and non-stationary important? Well, to tell you time series, in order to predict values in the time series, your data must be stationary. If the data is not stationary, you need to change it, convert it into stationary data. Well, in order to make a time series data, we perform differencing. Differencing is a method of subtracting, transforming a non-stationary time series into stationary one. We subtract the current value and the previous value of the time period, and that's how it goes on for the next data. What is correlation? Correlation is the association of two variables. I mean, how closely the two variables are related. Like, let's, for example, we have a salary hike and expense. Well, tell you in my case, if the salary is hikes, I would keep on my expenses will also rise. That's like linearly proportional for me. Well, different people might have different perspective for this, but for me, it's like yeah, salary hike is directly proportional to expense, directly related. Moving ahead, what is autocorrelation? Well, autocorrelation is the correlation with itself. I mean, autocorrelation can be defined as the correlation between itself and the other values of the same variable. What I mean by that is, for the time period, we may have two or more variables, and for the same time period, we will be finding out the correlation between different variables. I mean, how different variable is related to each other for the particular time period. I mean, we have partial autocorrelation. Partial autocorrelation is at lag k is the correlation that results after removing the effect of any correlation due to shorter lags. Well, partial autocorrelation is the conditional correlation. It is just like an interviewer asking you what was your contribution to making of the whole project. We are just neglecting the smaller price. We are directly, mean, rather than going long way, I'm just directly saying my individual contribution to the whole project. White noise. Well, a time series is white noise if the variables are independent and identically distributed with a mean value of 0. This means that all variables have the same variance and each value has a 0 correlation. Well, white noise is very important because If we have white noise in the data, it makes predictability harder. Also, the series of error remains that remains after forecasting model should ideally be the white noise. I mean, the error should be as low as possible, and that error should reflect white noise in order for a model to be very accurate. Autoregressive model. Autoregressive model is nothing, is just similar to linear regression that we have. So autoregressive model predicts the outcome variable at some point in time related to predictor variable x. Moving average model. As discussed earlier, moving average is the average of previous values for the particular term. So this model also depends on the averages over the period of time. ARIMA model. ARIMA model is nothing but the summation of autoregressive model and uh, moving average model. It takes comprises of three components. P is the order of AR term, Q is the order of MA term, D is the number of differencing that it can fit. So that's pretty much about theoretical aspect of time series analysis. These are some links that will help you and guide you through the course material, and that's it for the theoretical part. So mm, let's move on to the practical part that we are going to do cover. So we are going to do the time series analysis on air passengers data. So, let me show you the data set which I have. So we have this data set, air passengers data, which contains two columns, which is month and passengers. So the overall value is 144 passengers, 144. I mean count over the over the time span of time varying from 1949 to 1960. So let's start with the mm, no, predicting model or creating the model. So I'm line item one is just the importing in important packages like import pandas, numpy, matplotlib with the aliases, and I have also installed pmd arima. Now here I am loading the data set, and here I am checking whether the data set has loaded correctly. Now, when you go when you search for the info, we have number of rows 144, total entry as 144. We have two columns, months and passengers, both as null value, and then data type of these columns are date time and integer value. When we describe the model, describe the data set, we have count as 144, mean, standard deviation, minimum value. Here I am checking earlier in the info part, it already said that there was no null value. But still, for the sake of some just writing the code, I have checked whether there is any null value or not. Now what I'm doing is I am modifying the data set and converting. I mean, I am converting the month column as index, and I am creating TS as a new data set. Now we can see that the data has month object as index and passenger as the column. Simply plot the data and analyze visually. Now what I'm doing is I'm plotting I'm plotting the passengers column and checking what's the how does the figure looks like. As you can see from the above plot, it is clear that there is an increasing trend as more people take more flight. Now we need to check whether the data is station. We studied earlier, right? In order to proceed with time series analysis, you must have a data which is stationary. So in order to do that, we are moving. We'll check whether the data set that we have is mm, what we say stationary or not. So here, what I am doing is I'm going with I have defined a function using rolling statistics plot along with decay Fuller test results. So this is the method which I have written, and here I will pass instead of time series, I'll pass the data set like TS of passenger, right? We need to check whether the passenger column is stationary or not. Now you can see that p value is 0.99, and as a result of that, we have data is non-stationary. Now, now I'm doing determining the rolling statistics using rolling method for mean and standard deviation, and I'm plotting that in the image previously plotted, right? So this is how the image looks like. We can see. I'm really sorry. 1 minute. Yeah. So you can see that there is little change in standard deviation, but we have an increasing mean. Mean is clearly increasing, right, with time. This is not a so we can conclude that this is not a stationary data. Well, for a data to be stationary, mean has to be constant, and also since p value is greater than 0.05, so the data is not stationary. That was the threshold time. Now, how to make a time series stationary? Well, in order to make a time series stationary, we need to remove trend and seasonality. So, going by that, I have plotted. I'm doing log transformation here. So, I am creating a new data set with log transformation, and I have got this graph. We can again see that since there is a lot of noise present in the data set, we cannot uh, see the trends. So we need to use some smoothing techniques. Smoothing techniques refer to taking rolling estimates, that is considering the past few instance. What we are going to do is we are going to create simple moving average like earlier as discussed. Moving average takes into consideration the past values. So earlier in my example I used window size as 3. Since this data consists of data for the year from 1949 to 1960, so we will consider individual year. So for a year, we have the k value as 12. So I'm calculating moving average for this TS log data and then the mean. So when you calculate that, we can see that the mean is increasing. And when I pass this TS, since I've calculated the moving average for this, now what I'm going to do is I'm going to subtract, I'll do the differencing. So I will subtract moving average from the actual logarithmic data that we created, and we'll create moving new data set TS log moving average difference, and this is what we are going to pass into the into the function that we created. So now we can see that the data is stationary, but again here there is a drawback. Now we considered time period. We what we did here is like we consider time period to be strictly defined, which in this case yearly average, right? But in many a times we won't be having a defined time period like forecasting stock price. So we need to come up with some certain number. This is the reason why we take weighted moving average. So weighted moving average, I calculated weighted moving average here, exponential weighted moving average, and the time total was 12, and then I plotted it. So now what I'm doing is I am again doing the differencing here, and I'm subtracting weighted average from the logarithmic data that we created. Now again, I'll check for the stationarity. Now, now we have lag used as 13, and this time series has even lesser variation in mean and standard deviation in magnitude. Also, test statistics is smaller than the critical value, and p-value is less than 0.05, which is very less than 0.05. So this data is stationary. Now what we need to do is remove the trend and seasonality. Okay. So there are two ways of removing trend and seasonality. One is by differencing. So what I'm doing is I am taking TS log and TS log shift, and I'm doing the differencing. This appears to have reduced trend considerably. As you can see, this looks like a straight line to me. Uh, so this appears to have reduced the trend. Well, let's move ahead and use the function that we created. Now again, but now for this data set, what has happened is now again the p-value has increased from the threshold value 0.05, and hence the data is non-stationary. We can see that the mean and standard variations have small variation with time. Also, the statistics is less than 10% value. So differencing did not work. Let's move ahead with decomposition. Well, decomposition is nothing but we need to decompose the data into different components of the data set, right? Time series analysis, like trend, seasonal, residual components. So what I'm doing is I'm creating a new decomposition data, and I'm passing TS log, and I'm doing additive decomposition. So this is how I got trend, seasonal, and residual, and I'm plotting. And this was the original data set. Now what I'm doing is I'm checking whether the trend has any impact on that. I mean the trend. We decomposed the data into trend for the additive decomposition. I'm passing that trend here and checking whether it has any change. So we can see that in case of additive decomposition, the trend seems to be increasing, and also seasonal aspect is kind of huge. Residual has a way. So now what we need to do is we need to remove the trend. We have the increasing trend. So we will be removing the trend from the logarithmic data set that we had. So once that has been removed, we will pass this data into our function that we created and again check if the data is stationary or not. Now we can see that there is a significant change and the data is now the time series is stationary and there is no trend or seasonality. But again, let's decompose the same data again. I mean, we will pass TS log decompose here. I mean, the new data set that we created by differencing. After subtracting the trend, we remove the trend. So the data, that data we will be passing it into this model. Now pass. Now again, let's find out trend one, seasonal and residual for this data. Now, when we plot this, when we pass the trend one and plot the data, we see that the line seems to be constant. There is no increase or decrease in the trend. Also for the seasonal part, we can see that seasonality has also been significantly reduced. So let's go ahead with the plotting of ARIMA model. We have created auto correlation and partial correlation here. So now we will use auto ARIMA model, which will directly pick the best hyperparameter for time series modeling. So we need here we have divided the data into train and test data set, and 70% of the data has been used as train data, and the rest has been used as test data. So we have 144 different. Now I'm going to pass just train data to auto ARIMA model, and then again fit this train data. Now you can see that when the parameter is 111, order of 111 and seasonal order of 112, the auto arima has the best output. The model has the best output. So we'll do the prediction. Now here I am going to pass the test data set. So once that has been done, we'll plot the graph. As you can see in this graph, this line represents the training data set, yellow line represents the test data sets, and the green line represents the predicted value. So you can see that the predicted value is very close to the test value and fits the line. I mean, fits the trend and seasonality, kind of. So we can say this is one of the model that we made is uh, accurately reflecting the data trend and the time series analysis. So I hope you guys have understood the concept, and that will be all for today. If there is any questions or any doubts that you would like me to clear on, or you would want me to make a video on, do let me know over comment and chat, or you can directly mail me at my email address, which I'll be providing in the description. So thank you all, and that's it. Thank you.